Hello, I'm Abdul Raheem, a 9-pointer from IIT Bombay. In this video, we will start solving end semester questions from ordinary differential equations of spring 2021. In this video, I will be solving 2 questions, and in the upcoming videos, we will be solving more and more questions from this end semester examination. Here is the first question. For solutions of linear homogeneous differential equations in standard form with continuous coefficients on that interval I, the Wronskian is either never 0 or identically equal to 0 on I. This follows from Abel's identity, Lorentz cancellation law, Lipschitz continuity, and Picard iteration. The answer to this question is actually Abel identity, because that equation actually helps us to prove these statements. Okay, now for that, I will first of all write what this Abel's identity is. The Wronskian of function fg at the point x is equal to Wronskian of the same two functions f and g at any point a into e raised to minus integral a to x p of t dt. This is the Abel's identity for the differential equation y double prime plus p of x into y prime plus q of x equal to 0. So this is a linear homogeneous differential equation. Okay. Now, how does this equation actually help us prove that? The statement states that if Wronskian is 0 at any point, then it is identically equal to 0. And the other case possible is Wronskian is 0, not 0 at all. Okay. Now, one possibility, that's okay. Wronskian is not 0 at all. One possibility. Wronskian is not equal to 0 for any x. You can take any x in that interval, but Wronskian will be non-zero. That's one possibility. Okay. Now, suppose Wronskian is 0 at some point. Okay. Let's say at some point C, Wronskian is 0. Wronskian of fg at the point C is 0. Okay. Now, what does Abel's identity give us? Wronskian at any point is equal to Wronskian at a fixed point. The left hand side of the equation gives a function Wronskian, and the right hand side have first term as Wronskian evaluated at some point a into exponential of something something. Okay. Actually, the Wronskian function can be written as Wronskian at some point into some exponential function. Okay. So here what we will do, we will take this value c in place of a. Now what will happen? We will have the Wronskian function at any point equal to Wronskian at that point c. Okay, that is Wronskian of f and g at the point c into e power something. That doesn't matter, whatever it may be. We know that this is equal to 0. Okay, into exponential of something, whatever it may be. This is again 0. That means we got that Wronskian is identically equal to 0, or Wronskian at any x value in that interval equal to 0. Okay, I hope it's clear. So this Abel identity helps us to solve this question and also to prove the statement given in the question. So the correct option is Abel's identity. Okay. Now we will be going to the second question, that is, suppose y1 and y2 are two real valued linearly independent solutions of a second order linear homogeneous differential equation in standard form with continuous coefficients defined on some open interval. Then there is a unique 0 of y1 between any two successive zeros of y2. We have to select whether this statement is true or false. Okay. The claim is, suppose y1 and y2 are two linearly independent solutions of dash dash dash. Then there is a unique solution of y1 between any two zeros of y2. Take two consecutive zeros of y2. You can find exactly one zero of y1 in between them. That's the claim. So we have to say whether it is true or false. Okay. Now, due to some specialities of this y1 and y2, it is actually true, and I will show you a rigorous proof of that. Okay, so let's get started with the proof. So they are talking about two successive zeros of y2. Okay, so let me just take them as a and b. Let a and b, I will take b as a bigger one. Okay, let a less than b. These a and b are zeros of the function y2. Actually, I have to write let a and b, they are two different zeros of y2 with the property that b is greater among them. Okay. Now they claim that we can find some 0 of y1 in between a and b. Okay. Now let's take the case if this function y1 is non-zero for all x in between that a and b. I am claiming if the thing happened that the function y1 is not 0 completely between that interval a b. Let me check if that thing is actually possible. Okay, if that thing happens, I can define a function y2 by y1 on the interval closed interval ab. I will explain why this can be done. Okay, in the open interval, I can define this because in the open interval, we have assumed that this y1 is non-zero. But why on closed interval? I will explain that. Okay, so we have our Wronskian. What is Wronskian? Wronskian of y1 and y2 at the point x is equal to y1 y2 prime minus y2 y1 prime. Okay, and we know that since y1 and y2 are linearly independent solutions, this Wronskian cannot be equal to 0 at any point. Okay, so we already know that A is a solution. A is a 0 for A. That means y2 of A is equal to 0, and similarly y2 of B is equal to 0. Which means the second term from the Wronskian will be equal to 0. But we cannot have the entire Wronskian being 0 because y1 and y2 are linearly independent. So that will give us the result that this term has to be strictly positive or negative, not 0 for sure. Okay, so in that case we can say y1 of A cannot be equal to 0 and it will not be 0 in any case. Similarly, y1 of B also will not be equal to 0, which means we can define f of x as y2 by y1 on the closed interval ab. Okay, now tell me, what is f of a? F of a will be y2 of a divided by y1 of a. But y2 of a is 0, so f of a is 0. Similarly, f of b will also be 0 because y2 of b is 0. Okay, so we have a function which is defined on a closed interval and it has both n values being equal to 0. Do you remember any identities from calculus that we can apply here? We can use Rolle's theorem and say that there will be some point in between where the derivative will be 0. Right? Yes, exactly. So there will be some c in the interval ab. How can I say that? By Rolle's theorem. Okay. There will be some point in between a and b such that at that point the property satisfied will be that the derivative will be equal to 0. Okay, derivative will be exactly equal to 0 at some point c between a and b. Now, is there an issue with happening this? Yes, there is an issue. I will show you exactly what is that. What was our function f of x? F of x was y2 divided by y1. Let me just calculate the derivative of f. F prime is equal to, so we will start with denominator into derivative of numerator, that is y2 prime, minus numerator into derivative of denominator will be y1 prime divided by denominator square or y1 square. Now just check what is this numerator, y2 y1 y2 prime minus y2 y1 prime, which is actually our Wronskian of y1 y2, right, divided by y1 square. Okay, now what we have found is there will be some point c where this f prime will be equal to 0. We have f prime of some point c equal to 0. F prime is 0 means our Wronskian should be equal to 0 at that point, right? Yeah, because f prime is Wronskian divided by y1 square. So Wronskian has to be equal to 0 at that point. Is that really possible? No, this is not possible. Why? Why Wronskian cannot be equal to 0? Because we have y1 and y2 being two linearly independent solutions. So this is not possible. Okay, so we have got a result which is not possible. Why? Because our assumption was wrong. What was our assumption? This y1 is non-vanishing on open interval ab. This was our assumption which went wrong. Okay, so that means there must be some 0 of y1 between a and b. Okay, but in the claim in the question, they says that there is a unique 0. Now we have proved there will be some zeros, but now we have to again prove that it will be unique. Okay, so it's sure that y1 has at least one. That's for sure. That's already proved. At least one 0 on the interval ab. Now we have to show that it's unique. Our claim is unique. Like I am claiming that 0 will be unique. Okay, suppose there are two. Okay, in order to show something is unique, we will assume that there are two zeros. Okay, so suppose alpha comma beta are zeros. Let me assume that there are two different zeros of y1. What does that mean? That means y1 of alpha equal to 0 and y1 of beta equal to 0. Okay, now we will be doing a similar treatment as we did earlier. Okay, so we have this y1 being equal to 0. So I will define a new function g. G being equal to y1 divided by y2. Okay. Now we have this alpha and beta in this interval AB, which means A will be, this inequality will be satisfied if I assume this alpha is smaller than beta. I am claiming that alpha and beta are two different zeros. One can be smaller than the other in any order. So let me just assume this alpha is smaller than beta. Okay. Now in that sense, I have this inequality and I have G is equal to y1 divided by y2. Now let me check what properties does this function have. This function at the point alpha and beta will be equal to 0. Why? Because we have y1 at alpha equal to 0 and y1 at beta equal to 0. So G will be 0 at y1 and y2, and this can be, this function G is defined on the interval alpha comma beta. Okay, we will define this on the interval alpha beta. Now let me just calculate what will be the derivative of G prime of x will be equal to y2 y1 prime minus y1 y2 prime divided by y2 square. You can check that the numerator is actually the negative of Wronskian. It's actually equal to negative of y1 y2 divided by y2 square. Okay. Actually, we can apply Rolle's theorem on the function g, right? Because on the endpoints alpha and beta, it is equal to 0. So by Rolle's theorem, applying Rolle's theorem, we can say that g prime will be equal to 0 at some point d. The derivative will be 0 at some point d belonging to alpha beta. Okay. But what is g prime being equal to 0 implying? G prime being equal to 0 will say that Wronskian will be equal to 0. And this is not possible because of the reason I had already explained earlier. What is that? Y1 and y2 being linearly independent means their Wronskian cannot be equal to 0 at any point. Okay. So again we have arrived at a contradiction. Why? Because we assume that there will be two distinct zeros. Okay, we assume that alpha and beta are two distinct roots, which is not possible. That means our claim is true, or we have a unique solution. So from this second contradiction also, we can say that y1 has unique zero between two zeros of y2. Okay, this proof is completely done. Let me just summarize the proof. Okay, what have we actually done? Firstly, we assume that, consider the case of y being not equal to 0 at every point. That means there will be no solutions of y1 between two solutions of y2. Let us check if that is possible. So we consider this function y2 by y1 and found a contradiction which said that there will be some root of y1 between this a and b. Okay, so once existence is proved, there can be more than one also, right? But we need it to be unique. So I considered two different roots alpha and beta and again found a contradiction. Okay, so that means there cannot be two zeros of y1 between two successive roots of y2, which means that should be a unique zero of y1 between two successive roots of y2. I hope the solutions were really useful and understandable to you. Thank you for watching the video. Stay tuned to the channel, subscribe to the channel. We will be uploading the video of more and more questions. Thank you for watching the video. Stay subscribed to the channel. I will be solving more and more questions from the end semester examination in the upcoming videos. Join the Telegram channel and Instagram account to get live updates. Thank you.